the research is focused on spectroscopy, and that was throughout introduced by my colleague in his previous talk. And regarding the approaches, the other part of our research is based on different microscopic techniques. So we study different processes related to the cytoskeleton, and in that we use TIRF microscopy, about which my talk is. And besides this imaging approach, we also have kind of standard confocal microscopy and kind of other super resolution microscope, the structured illumination microscope, the SIB from Zeiss. And a bit related to spectroscopy, we also have at the Santa Agata Research Center the Raman microscope. So these are the approaches that we are using in page to address the different biological questions that we are interested in. So now let me guide to microscopy from the spectroscopy approaches that were introduced by my colleague. So actually I choose one of the techniques that we routinely use in our research, that is total internal reflection fluorescence microscopy. So this technique is based on the unique field of the evanescent field that is formed upon total internal reflection of the light incident to the boundary of two media with appropriate refractive indices, and provides a better resolution than what we can expect from the standard fluorescence microscopes. And actually the use of total internal reflection in fluorescence microscopy was one of the earliest ideas behind what we call today super resolution microscopy imaging. Okay, so to give an outline about my talk, first of all I would like to briefly explain the rationale for developing these so-called super resolution microscopy techniques by briefly discussing the classical resolution limit of the light microscopes, and then I would introduce in details the total internal reflection fluorescence microscopy, or TIRF microscopy, some of the historical perspectives, as well as the physical principles and some technical considerations that you have to think of when you want to use this technique maybe for your own research. And at the end, to illustrate the potential of the technique, I will show you different applications from the fields of protein biochemistry and cell biology, and some special applications related to micropatterning and single molecule localization imaging. Okay, so to introduce the concept of super resolution microscopy imaging, we have to go back to the 1870s, when the diffraction limit theory was actually formulated first by Ernst Abbe. And this theory tells us that the resolution limit of a light microscope, that is how small things we can see or distinguish on the image, is inherently limited by the wave nature of the light. So if we want to image, for example, a point-like object that is shown here, the image will not be an ideal point. However, the image would be an interference pattern generated by diffraction. So the original structure, that's an ideal point, is spread in space. So this is how we can imagine in the XY, the lateral direction, and also in the axial, the Z direction, the image, what we get. So our objects are distorted by the point spread function when we are trying to image them a light microscope or a fluorescence microscope. This can be also formulated, and some numbers can be derived. So the main principle is that the resolution of a light microscope depends on the wavelength. So the smaller the wavelength is, the better the resolution. is, and it also depends on a parameter that we call the numerical aperture. That's characteristic for the lens systems, the objective and the oculars that we use for imaging. So the higher the numerical aperture is, the better resolution is. And in terms of numbers, we can get something like 200 nanometers in the axial direction, and in the lateral direction, and in the Z, the axial direction, the resolution is somewhat worse. We get around 800 nanometers, so we cannot see smaller things than these distances. And that limitation actually inspired the scientists to find out ideas or kind of tricks that can be used to improve the resolution of fluorescence microscopy. So yeah, I'm saying fluorescence microscopy because all of these techniques are fluorescence microscopy based techniques. So the first one was actually the confocal microscopy from 1961, developed by Marvin Minsky. And in the confocal microscope, to simply explain, the idea is to use a pinhole or a aperture that acts as a spatial filter, which will filter out the light from the out of focus planes. So that will result in an improvement in the axial resolution to approximately 500–600 nanometers. The second one was the total internal reflection fluorescence microscopy that was combined with fluorescence. So the technique or the phenomenon was combined with fluorescence in 1981. And after that, in 2000, the stimulated emission microscopy was introduced by Stefan Hell. This is, we can call it a point spread function engineering technique. So here the improvement of the resolution is based on the use of two lasers. One will excite the fluorophores and the other one will actually stimulate the emission before collecting the spontaneous emission from the fluorophores, and therefore the point spread function can be reduced to a few tens of nanometers. And that was followed by single molecule localization microscopy techniques in 2006. Here, one technique, the storm, appeared in a publication noted by Eric Betsy, and also so this technique requires special fluorophores, the so-called phototransformable fluorophores, and in that William Lerner achieved some developments. So the idea is to image individual fluorescent molecules with quite low density, and then fit the image of these individual fluorophores with a Gaussian function to be able to localize the exact XY coordinates. And the last one is the structured illumination microscopy from 2008, and here the idea is to image the sample through a rotating grid, and then comparing the sample, the different images and the position of the grid, and doing some mathematics, we can get an improvement, a two-fold improvement in the resolution. Okay. So these two techniques, the stimulated emission microscopy and the single molecule localization microscopy, the storm, stochastic optical reconstruction microscopy, and the PALM, photoactivated localization microscopy techniques are highlighted because these techniques were awarded by the Nobel Prize 2 years ago. Okay, so now let's go back to total internal reflection fluorescence microscopy. So actually the phenomenon, the total internal reflection, was initially used in visible and infrared absorption spectroscopy to study the photophysics of materials near surfaces. To the microscopy, the phenomenon was introduced first by Ambrose in 1956, this is the original publications. You can see schematically the principles are shown here, and we use this technique to visualize cellular regions which are close to the glass surface. The technique was combined almost 20 years later by Daniel Axelrod with fluorescence microscopy. That is the original publication of the use of total internal reflection in fluorescence microscopy. And here again, what was highlighted that with this technique, the cellular regions which are close to the surface, to the cell glass contact, can be visualized. Okay, so let's go a little bit to the theory. So what are the principles of TIRF? I'm sure that all of you know these basic principles, what is happening to the light when it hits the boundary of two media with different refractive indices. So it can be refracted or it can be reflected. Now if we consider that the refractive index of the first medium is larger than the refractive index of the second medium, from Schnell's law of refraction, what we can predict that the angle of refraction, this alpha 2, is larger than the angle of incidence. So at this point we can think that if we increase the angle of incidence as it's shown here, the angle of refraction increases as well. So at a situation what we call the critical angle as the angle of incidence, the angle of refraction will be parallel to the boundary of two surfaces or the two media. And if we further increase the angle of incidence, we get total internal reflection, so the light is reflected from the two surfaces or the boundary of the two media. And the critical angle, as shown by this equation, can be related to the refractive indices of the two media. Okay, so to understand what is happening exactly in case of total internal reflection, we have to go to the theory of the wave theory of light. Because if you look at the Maxwell's equations and we solve them for these conditions, the solution will predict the formation of an electromagnetic field that is actually called the evanescent field or an evanescent wave. Okay? Yeah, and yeah, this is how if you illuminate before going to the wave theory. So that's a glass air boundary, and here you can see that the light is reflected upon total internal reflection. Okay. Yeah. So considering the wave theory without going deeply into the math, if we consider that the transmitted beam here is a monochromatic plane wave, then we can use this equation to describe the electric field of this plane wave, where the E is the electric field, R is the direction of propagation, T the time, K is the wave vector, and omega is the frequency. So simply considering that we decompose the electric field into two directions. One direction is the direction which is parallel to the boundary of the two surfaces. This is what we call the X. And the other one, which is perpendicular to the boundary, that is what we call the Z. Considering the law of refraction, we can relate these two components, the Z and the X component, to the angle of incidence and the refractive indices of the two media. So you don't have to remember the equation, just these simple things here. If we analyze how the Z and the X component is altered under different conditions in terms of the angle of incidence, what we can see is that when the angle of incidence equals to the critical angle, then the Z component disappears, and actually what we have is only the X component. So we have an electromagnetic wave which propagates parallel to the surface. Now if we go to the supercritical angles, that is the angle of incidence is larger than the critical angle, then the z component becomes real and can be described by this part of the equation. So here one important thing that it follows an exponential function in the z direction, and also it decays, this tells us that it decays exponentially from the boundary of the two surfaces. So when we have total internal reflection, an evanescent electromagnetic field appears in the second medium. We can derive the intensity profile of this evanescent field, which is shown here. So it decays exponentially from the boundary of the two media. At the boundary it has the maximum intensity denoted by I0. And also we can see this parameter, this d here, d, what we call the penetration depth or the decay length of the evanescent field described by this relation here. So the main thing is that the penetration depth can be related to the refractive indices of the two media, okay, and also the angle of incidence. And yeah, so this figure highlights the behavior of the evanescent electromagnetic field, how the intensity decays exponentially. And actually, if you consider this exponential decay from the surface, you can easily understand how it can be used in a fluorescence microscope. So if you imagine that this line here, the zero distance, corresponds to the surface of your, or the boundary of your sample and the glass. So you will have this evanescent field only near to this boundary, so you can illuminate, if you consider the evanescent excitation field, you can illuminate your fluorophores in the sample only within this narrow region that decays within a few hundreds of nanometers. And if you compare with the wide field illumination that is schematically shown here, then with wide field fluorescence imaging you will illuminate through your sample all the layers in the whole thickness of the sample. Okay, so there are actually some important things that can be useful to note. So these can be useful if you want to set up your TIRF microscope or you want to set up your experiments. What is that you have to consider? Okay. So one thing is how the critical angle depends on the refractive indices of the two media. So actually it can be derived from the ratio of the two refractive indices, which is plotted on the horizontal axis, and the corresponding critical angles are shown on the vertical axis. And what you can note from this figure, if the two refractive indices are equal or close to each other, then the critical angle is quite high, 90, close to 90 degrees. However, if you start to increase, for example, that's one way, start to increase the refractive index of the first medium, then you get a lower ratio, which also means lower critical angles. The other thing that can be useful also in planning experiments, how the evanescent nature of the field formed in the second medium is affected by different parameters. So the first one is the angle of incidence. I have shown this equation here. The decay length depends on the angle of incidence. And what you can notice from this figure is that if you increase the angle of incidence, then the decay length or the penetration depth of the field decreases as well. So if you want to have a smaller penetration depth that would give you a higher resolution, then you want to use a larger angle of incidences. Also, the second thing is that the decay length depends on the wavelength. So as you can see from this figure, if you increase the wavelength, so from this curve to the other ones, it means that the decay length increases. So again, if you want to have better resolution, then you want to choose a lower wavelength, but that also comes from the classical theory of the resolution limit. And the other thing is how the decay length of the evanescent field depends on the refractive index of the sample. That is what you can see here. So if we look at one curve here, what we can notice that if we increase the refractive index of the sample, then the decay length will increase as well. And the other thing what you can note here is that if you increase the angle of incidence, which is shown here, so these curves were calculated for different angles of incidences. If you increase the angle of incidence, what you can notice that the decay length of the evanescent field becomes less sensitive to the refractive index of your sample. And that can be useful if you imagine that inside the cells that they can be different regions with different refractive indices. So then you want to have a higher angle of incidence to be sure that inside the cell everything is homogeneously illuminated by the evanescent field. Okay. Okay, so let's sum up what we know so far about the total internal reflection fluorescence or evanescent wave microscopy. So I introduced the formation of the evanescent wave and some essential properties that are used in this microscopy technique. So it decays exponentially in intensity with increasing distance normal to the surface. The decay length is in the order of the wavelength, so in a few hundreds of nanometer that you can adjust by adjusting the angle of incidence and also the refractive indices. And this is the evanescent wave. Since the evanescent wave is formed at the boundary of two media, such as the glass cover slip and the sample that you investigate, the evanescent field can excite only the fluorophores, which are located within this region, within this few hundred nanometer thick region. The other fluorophores will not be excited, so therefore you cannot detect fluorescence emission from the deeper regions of your sample, only the regions which are close to the boundary of these two surfaces. And it also means that actually you will eliminate the kind of out of focus fluorescence or background fluorescence by simply not exciting those fluorophores in the sample. Okay? So TIRF is a near-field imaging method that can provide better resolution that can be achieved by the classical fluorescence microscope in the range of a few hundreds of nanometers, so 1–200 nanometer resolution that you can have, and that based on the unique features of the evanescent field. So here maybe one note here is that the resolution is different in the lateral and the axial direction, so this improvement of the resolution using the basic TIRF technique can be reached in the axial direction in depth. Okay? Okay, and now let's see how we can imagine our sample if we want to image by TIRF illumination. So this can be a kind of textbook images which illustrate the difference between the conventional wide field and TIRF illumination. So this is a cell illuminated by wide field, so you can see, of course, the cell. But if you illuminate with TIRF microscopy, what you can notice that this huge background fluorescence that comes from deeper layers of the cell simply disappears, so you can see more details from the regions which are close to the surface in or near the plasma membrane. This second image highlights that can happen that sometimes in TIRF you will see or you will resolve different structures which are otherwise not visible in a wide field image. So this is a wide field image of the microtubule cytoskeleton. This is the TIRF microscopy image, and this is the merge. Hopefully the contrast is good enough to see that the red region corresponds to the TIRF image, and the green region, which corresponds to the wide field image, does not significantly colocalize. And also another pair of images, actually that's related to our research, which is focused on the cytoskeletal polymer dynamics, including actin and microtubules. So this is a cell-free system that contains actin filaments, fiber-like structures, and when we illuminate with wide field microscope, this is what we can see. Maybe you can see that there are some filaments, but clearly you cannot distinguish individual filaments. However, if you switch from the wide field to the TIRF illumination, you can nicely resolve individual actin filament, and that would be the same for microtubules as well. Okay. And yeah, and this is just a movie that. Okay, so this is a movie that shows what we can see if we go from, in case of an epi, fluorescence illumination, we go from wide field to TIRF illumination, and what you can see on this movie are fluorescent microspheres, which are diffusing. So this is a wide field illumination, and if you start to increase the angle of incidence, then actually suddenly you will change to the TIRF illumination. And if you have a well properly aligned system, you will see this sudden transition from kind of high background to low background regime. Okay, so due to the nature of the evanescent field, as I mentioned, this technique can be used mostly to image or study processes which are close to the surface, in the cell membrane or near the cell membrane. So, for example, the dynamics and the structure of the extracellular matrix can be investigated, the cell surface context, or the properties of the cell membrane, different ion channels, exocytosis, endocytosis, and also the cytoskeletal elements inside the cell but close to the plasma membrane. Also, one good thing with TIRF is that it can be combined with other approaches, and then the advantages of the two approaches which are combined are also combined. So if you combine, for example, TIRF microscopy with the fluorescence recovery after photobleaching, you get information about the diffusive behavior of the surface closed structures. You can also combine with fluorescence resonance energy transfer, or the technique was used in combination with atomic force microscopy. It was the basis for single molecule localization techniques such as STORM and FARM. Another very powerful approach is to combine the TIRF microscopy with a technique what we call micropatterning. If I have time, I will introduce briefly what's the principle of this technique that allows us to generate different surface chemistries and different patterns on the surface, which can be useful in some applications, and also microfluidics. Okay, so now let's see briefly some technical considerations. So if you have, actually the first TIRF microscopes were homemade microscopes. So if you want to upgrade your fluorescence microscope to a TIRF microscope, what do you have to consider? So first of all, one thing, you have to consider that in the microscope, the total internal reflection has to happen. So for that, you want that the sample that you investigate has a lower refractive index than the other media, which is usually glass, that is coupled to the objective by immersion oil. So usually this condition is fulfilled. Because in general, we can consider the refractive index of the cell is 1.36 and the refractive index of the glass or the oil is 1.515. So this condition is fulfilled. The most important condition, or actually what is technically more challenging than the first one, is to be sure that the angle of incidence is in the supercritical regime, so that is higher than the critical angle that is required for total internal reflection to occur. And if you look at these numbers, so if we imagine the glass-water interface, the critical angle would be something like 61, while if we imagine the glass-cell interface, then the critical angle is almost 64 degrees. Okay, so this is the microscope system that we have at the University of Pécs. So that's the microscope stand is from Olympus. That's an IX81, and we have as light sources we have two lasers here, which are coupled to the stand via the rear port of the microscope. We have also the optical elements which are required to produce the supercritical angles, and that's an objective-based TIRF microscope. And also for the detection, what we have is a Hamamatsu Orca CCD camera, but of course for special applications you can choose, or you have to choose different detectors, maybe more sensitive EMCCD cameras. Okay, so actually TIRF can be done by a lamp, not only by lasers. And these are two figures which schematically show the configuration for the lamp-based TIRF illumination. Here the main principle is that you want to discard the subcritical illumination, because that would create you the high background that you don't want to see in TIRF microscopy. And that scheme was proposed by Daniel Axelrod. So here an off-axis slit is used that will allow only the illumination at supercritical angle to pass towards the sample and illuminate the sample here. And this is a commercial setup that was proposed by Olympus. That is based on the use of a wedge prism and an off-center slit. So the wedge prisms can deflect the light at different angles. So first of all, these prisms will deflect the light, and then the light, which is the supercritical regime, can go through in this off-center slit, so that ensures us the TIRF illumination. Okay. So one thing that if you use a lamp, then it's easy to select the wavelength for the excitation simply by introducing filters. The other thing is that you discard most of the excitation lights, so the excitation intensity is relatively low, and therefore the lamp-based TIRF configuration is mostly useful if you want to image intrinsically bright samples. The most commonly used TIRF setup is based on the illumination with lasers. These are two, again, figures which shows that the laser can be introduced into the microscope via a side port or via the rear port by using different optical elements. So the laser beam has to be focused to the back focal plane of the objective, which is done by focusing lenses. And relatively simply, just by changing the position of the laser beam, the illumination or total internal reflection can be achieved. In the system, what we have, we can combine 4 different laser lines. We have, at this moment, we have only two, a 491 and a 568 laser line. And also, in most of the commercial setups, you can adjust the properties of the laser beam in terms of total internal reflection using the software. So you can individually adjust the fiber position, the penetration depth, put the refractive index of your sample, and then the software will compute what will be the best critical angle for you, but usually, at least in our system, we have to adjust a little bit. Okay, yeah, so regarding the optics, the first solution to achieve the subcritical illumination was based on prism. So the first TIRF systems were prism-based TIRF system, as one of the solutions can be seen on this figure here. So this is the laser, and then the laser is directed upwards and then to the sample. So here and on the sample what we can find is a prism. It's enlarged here. That was the first solution proposed by Daniel Axelrod. So the prism is coupled to the sample by an immersion oil. So by positioning this beam director here and the focusing lens, the light can reach or enter the sample at angles which are larger than the critical angle for these two media. So in this case, what you can note is that the cells are actually on the upper cover slip, okay, because the adolescent wave is formed here and then imaged by the objective from the other side. So in this setup, what you cannot do is to manipulate the sample in the experiment. So that's one disadvantage of the prism-based TIRF system, that you cannot change the composition of the sample. Of course, other solutions are available where you can, the laser is introduced from the bottom, so you can have access to your sample, which can be important if you want to, for example, micro-inject your cells or change the protein content in your sample. Most commonly used are the objective-based TIRF microscopes. This is again one of the setup that is available. So here the laser is directed through the objective, and this is where the evanescent field is formed, and then it's an epifluorescent illumination, so the emission is detected on the same side. The position of the laser beam can be adjusted by either a micrometer or by the software, as I mentioned on the previous slides. Actually, what is happening to the laser beam is shown schematically here. So if we have a wide field illumination, then the laser beam goes along the optical axis of the objective. That will result in the illumination of the whole sample. So if you want to have the laser beam incident to the surface of the glass and your sample, you have to have the angle of incidence larger than the critical angle. And how it is achieved is that the laser beam is just put in an off-axis position. So here it's focused at the back focal plane of the objective, so it can be reflected to reach the sample in the supercritical regime, and that is this off-axis movement of the beam is done by the micrometer or by the software that will also change the position of the laser by a micrometer. Okay. So there is one important consideration for the objective-based TIRF systems, is that the numerical aperture of the objective has to be relatively large. So these are just numbers to illustrate that if you want to image something in a water-based sample, like a glass-water interface, the minimum numerical aperture that is required to be able to reach the supercritical angles for TIRF illumination is 1.33. You can see that it's relatively large. And if you do this calculation or think over this thing for the glass cell interface, what you can have at the end, that the minimum numerical aperture is 1.38, which is almost 1.4. So the numerical aperture of your objective has to be larger than this one, because otherwise you are not able to illuminate your sample in TIRF regime, at least with an objective. Okay. So I listed here some commercially available objectives. So the minimum that you want is 1.4, but you can get 1.45, 1.49, and the largest one is 1.65, but that requires a special immersion medium, as well as a special glass cover slip, which is quite expensive. So usually, I guess most commonly these two objectives, the 1.45 and the 1.49, are used in TIRF imaging. And what this table and also the figure highlight, that the higher the numerical aperture is, the more flexible you are in TIRF microscopy. So if you are at the edge, like for example using this 1.4 numerical aperture objective to image cells, so you consider the glass cell interface, the fraction of the numerical aperture that can be used to set the TIRF illumination is 0.02. So even if you have a well or perfectly aligned laser beam, it's really difficult to set and then to have any flexibility in your TIRF illumination. However, if you increase the numerical aperture, this fraction will increase as well. It's highlighted or represented on this image by these margins which are available for the TIRF illumination. So why is it important? Actually, this is my previous figure, which can also highlight the importance of the fraction of the numerical aperture of the objective that you can use for TIRF illumination. So, so if you have a higher fraction that can be used, then you have more flexibility in setting the angle of incidence. So that's the starting point. And if you have more flexibility to set the angle of incidence, that means that you can set higher angle of incidences, you can get a narrower evanescent field, so you can have a better resolution in TIRF microscopy. And the other thing is shown here. So again, if you can set higher angle of incidences, you get actually less sensitivity of the evanescent field to the refractive index of the sample.